Going back over here, this was supposed to be 16. Or another mistake, 12, excuse me. All right, and I think I did say 12 before, didn't I? I just wrote 8. So yeah, adding up 2, another 2 is 4, 6, 8, 12. 12 elements of order 4. Let's do more examples. Coming over here, external direct product of Z2 with Z2 with Z4. It does have 16 elements, 2 times 2 times 4. Elements of this external direct product have 3 components, A, B, and C. The possible orders for A and B are 1 and 2. The all possible orders for C are 1, 2, and 4. So if I was going to make a full table, let's see. Here's a systematic way of doing it. Watch for my mistakes. So you could also have order 4. I think I'm not going to make the full table over there for that example. Okay, so altogether 12 ways of having different kinds of orders coming together. Take the LCM in each case. You get 1, 2, 2, 2, 2, 2, 2, 2, 4, 4, 4, 4. Number of elements, how do you think about it? You go back here. Each of these has order 1 in this case. There's only one element of order 1. It's the identity, which we already knew. Go to the next row. 1, 2, 1. There's one element of order 1, 0. One element of order 1 over here, 0. Also one element of order 2. B is in Z2. The element of order 2 in there is 2. Excuse me, 1. So we get 1 times 1 times 1 is 1. Same with this and this. Oh, excuse me, just this one. 1 times 1 times 1 is 1. Actually, with all these ones that have just 1s and 2s, we have 1 times 1 times 1 each time. Because there's one element of order 1 in each case, and in each case there's also one element of order 2. Right, there's one element of order 2 in Z4 as well. That's the number 2. Am I matching up my rows correctly? Let me just write 1s from now on. I guess it's only one more. I'm going to go write it. Make sure things are matching correctly there. All right, on to this row. Looking at that one. One possibility there, one possibility there, 2 possibilities here. And there's going to be 2 possibilities for the other ones as well. All right, so the number of elements of order 2 oops, I'm not matching up right. Those are the elements of order 2, where the least common multiples 2. How many of them are there? 1 plus 1 plus 1, etc. 1, 2, 3, 4, 5, 6, 7. Did I miss that? Right? I can always check the answer at the end. There are 8 elements of order 4. 7 elements of order 2. 1 element of order 1. 8 total, or 7 total here. 8 total here. 1 there. Orders 1, 2, 4. Yeah, I'm not going to make the whole table here. Of course, you got the identity. The orders of A, B, and C, though, can only be 1s and 2s. So you don't really have to make the full table. You know, one example of something in the table would be this one. The least common multiple would be 2, but that doesn't matter. As far as the number of elements, you still have 1 times 1 times 1 times 1 is 1. Because there's one element of order 1 and one element of order 2 in each of these factors there. So every non-identity element is going to have order 2. It's going to be 15 elements of order 2. 15 elements of order 2. And nothing else. 15 cyclic subgroups of order 2 as well. Coming back to this example, we've got 2 factors in the external direct product. What are the possibilities here? This one's maybe a little bit more interesting, because when you have order 8, there are 4 generators of subgroups of order, cyclic subgroups of order 8. Those are the LCMs. Put it back over here now. 2 elements of order 4. So you get a 1 times 2 is 2. 4 elements of order 8. So you get a 1 times 4 is 4. Then a 1 times 1, a 1 times 1, 1 times 2, and a 1 times 4. So altogether there are, of course, 1 element of order 1. How many elements of order 2? 1, 2, 3 of them. How many elements of order 4? 2 plus 2 is 4 of them. And what's left? 4 plus 4, 8 elements of order 8. Is that up to 16? Double check that. Yes. Okay. So again, you don't have to organize your work in a table like this, but I think it's probably a good thing. Helpful. Okay. And I would count that as good work if I have a graded problem or an exam problem where you've got to do this kind of thing. Count the number of elements of each order. What these things do illustrate as well is that all these different groups, even though they all have 16 elements, they're all not isomorphic to each other, because you've got different numbers of elements of the various orders. And none of them are cyclic either. So in general, there are at least 1, 2, 3, 4, 5, I included the cyclic group of order 16. 5 groups of order 16. Are there non-cyclic or non-Abelian groups of order 16? These are all Abelian. Of course, yeah. There's, for example, D8. Symmetries of an octagon, regular octagon, that would have order 16 and be non-Abelian. Could you find other groups of order 16? Possibly. Okay. Here's a criterion for the direct product, external direct product of 2 groups to be cyclic. Let G and H be finite cyclic groups. Then the external direct product of G with H is cyclic if and only if the orders of G and H are relatively prime. The external direct product of Z2 with Z3 was cyclic. It was isomorphic to Z6. 2 and 3 are relatively prime. In each of these cases, the factors are cyclic, but the external direct products are not cyclic. The orders of these things are not relatively prime. 2 and 4 are not relatively prime. 2 and 8 are not relatively prime. And you can extend this to a finite number of finite cyclic groups. You have finitely many, like we have here in our examples. Corollary 2 is you can interpret this in terms of the z's. You can say, for example, the external direct product of, say, Zn1 with Zn2 with Zn3, etc., up to Znk, is cyclic if and only if, well, we should be a little careful here, each pair of orders is relatively prime. We could write GCD Ni, Nj equals 1 for all I not equal to j, going from 1 to k. That's how I can extend it and write it in terms of Z groups. In particular, if the n's are different primes, that would be an example. Or different powers. Powers of different primes would be another example. Doesn't come up in the reading, but it is a completion exercise. It's worth mentioning here. That the external direct product of groups doesn't depend on the order that you put the groups in the external direct product. For example, the external direct product of G and H and the external direct product of H and G are isomorphic. Even if G and H are not abelian, G and H can be any groups. What's an isomorphism? There's the most natural isomorphism. And it is an isomorphism. Just switch around the order. And this extends to any finite number of groups in your external direct product. Okay, that's worth knowing. So this group, for example, here is isomorphic to, for example, this is isomorphic to, for example, this. I guess those are the only 3 different ways of writing it. They're not technically the same groups, but they are isomorphic, so we sort of think of them as effectively being the same. More facts in the reading that you're going to make use of on homework and you should know for exams. This one's a little tricky. Suppose S and T are relatively prime. Then the U group, UST, the groups of units modulo S times T, is isomorphic to the external direct product of US and UT. And the tricky part is this next part. If K is a divisor of n, we define this thing, U sub K of n, to be everything in UN that when divided by K gives you 1 for the remainder. X mod K equals 1. That turns out to be a subgroup of UN. And we also have this fact. This is a subgroup of UN. That was a completion exercise, I think, back in chapter 3, to show that was a subgroup. Also have these isomorphisms. Okay? When combined with what I'm going to show you on the next slide, this can allow you to figure out the isomorphism class, you might say, of any U group. And by the way, this can be extended to a finite number of products of numbers in there that are relatively close to each other as well. For example, we might wonder what the isomorphism class of, oh, let's say 70 is. 70, do the prime factorization of 70. 70 is what, 2 times 5 times 7? Which are all prime, and they are therefore all relatively prime to each other. So this is isomorphic according to the extension of this fact to the product of more than just two things that are relatively prime. This is going to be isomorphic to U2, external direct product with U5, external direct product of U7. And I hope it makes sense that U2 is, well, not a band, but isomorphic to Z1. Just the identity. I like classic rock and roll, but it does to a large extent amaze me that all these really old groups still are really popular. I mean, they make great music, so it's understandable that way, but they are really old too. Guys from U2, maybe they're in the 50s. I mean, I think about the Rolling Stones. What are they, in their 70s? They're still performing? I don't know. Pretty amazing. Believe that? Certainly U5 has 4 elements. 1, 2, 3, and 4. U7 has 6 elements. 1, 2, 3, 4, 5, and 6. They are cyclic too. And since this is just the identity, which maybe I should call 0 instead of E, this is going to be isomorphic too. You can get rid of identities in your external direct product. Identity factors, meaning trivial groups is what I should say. U70 is isomorphic to that, and it's got 24 elements. Or their phi of 70 should be 24. Then you can check that out in Mathematica, if I have not made a mistake. This looks good. Here's some other facts that will be helpful in continuing this kind of decomposition. What do you do when you got a power of a prime? In general, you got a power. Well, if it's a power of 2, you have this fact. For powers of other primes besides 2 odd primes, you have this fact. Not proving these, the book. I think the book does not prove these. Leaves it as an exercise, but the book does prove the fact on the preceding slide. This could then help us, for example, figure out the isomorphism class of, say, U100. 100 having a prime factorization of 2 squared times 5 squared. 2 squared and 5 squared are relatively prime, so this is isomorphic to this. You have 2 squared. If this one, no, actually not quite. It's this one. When n has got to be bigger than or equal to 3 to use this one. U4 is isomorphic to Z2. 5 squared fits this one. P is 5. You get a 5 squared minus 5 first. 25 minus 5 is 20. This is going to be a Z20. And 2 and 20 are not relatively prime, so this is not cyclic. This is not isomorphic to Z4. That's a pretty cool thing, I think. Isn't it? Don't you agree? Can you figure out what the U groups are isomorphic to? Of course, you still also have my U group Cayley table calculator in Mathematica, if you want to make use of that. This thing here. Of course, if I go out to U, I don't let myself go out to U100 there, but you can see the Cayley tables for different ends. Of course, even though that can be helpful, it's really easier to use these isomorphism facts actually to figure out the isomorphism class than just looking at the table. Looking at the table is helpful in doing calculations, but these kinds of things are going to be extra helpful, perfectly helpful, you could say, to figure out the isomorphism class, at least once you figure out how to use them. All right, in the time remaining, we're going to start the next chapter. introduce the idea of a normal subgroup. Probably chapter 9 is the weirdest chapter. Okay? Normal subgroups are kind of a weird concept. But the weirdest concept is something called a factor group, also called a quotient group. I learned it as a quotient group, actually. That's the weirdest concept, but it's still a tool. It's still a tool for our classification thing that we're doing. Okay, these are all tools. You need to understand normal subgroups before you can understand factor groups, though. It's a little bit wordy here, but I think it's worth writing down all of this. A subgroup H of G is called a normal subgroup of G, or is said to be normal in G, if and only if AH equals HA for all A and G. A equals Ha for all A and G. In words, and this is important to think about this in words too, for every A and G, the left coset of H in G containing A equals the right coset of H in G containing A. Which seems a little weird to say that. They both contain A. They always contain A, no matter whether H is normal or not. But if H is not normal, they might not be equal to each other. This is denoted by the special symbol that looks like this. So the less than sign for subgroup notation becomes a triangle sign for normal subgroup notation. Okay, it's really not a less than. You take your subgroup symbol, and I guess we only do it with the strict notation here, and put an extra line on it. I've never seen anybody write this, but I suppose you could. Excuse me. I've just never seen anybody write it. It's always just been a plain triangle, keeping in mind that H could equal G. All right, so that's special notation for being a normal subgroup. Look at an example in a minute here. Evidently, this definition, if you think about it, holds up the possibility, at least, that being normal in is not transitive. What do I mean by that? I mean this. If K is normal in H, and H is normal in G, is K normal in G? Maybe, maybe not. Certainly if K is a subgroup of H and H is a subgroup of G, then K will be a subgroup of G. But if K is normal in H, a normal subgroup of H, and H is a normal subgroup of G, then maybe K is not necessarily a normal subgroup of G. I'm sort of holding out the possibility that the answer to this might be no. We will see. What's an example and a non-example? Or maybe a few if we have time. Well, easy examples are abelian groups. If G is abelian, then any subgroup of G is normal. I hope that makes sense looking at that definition. If G is abelian, and H is a subgroup of G, then in fact H must be a normal subgroup of G. A would equal Ha for any group elements. H would equal HA for any little H and H. So that's one trivial fact. Another pretty trivial fact is that for any group G, abelian or not, You can say the trivial subgroup is normal in the group. The whole group is normal in the group. And a little bit more, less trivially, the center of the group is normal in the group. Although that's still pretty trivial too. But remember the definition of the center, that's the only hard part. Slightly hard part. It should be not too hard, right? The center of G is the set of all things that commute with everything in G. This equation is going to be true for all H in the center and for any A in G. So every left coset will equal the corresponding right coset because of that. Put the definition up there. We already knew the center was a subgroup. Okay, that's important. That's part of the definition, really. Really, you should verify H as a subgroup first, but we already knew the center was a subgroup. It shouldn't be just a subset. We are talking about subgroups. What's a non-example? What's something that's not a normal subgroup? Simplest example I can think of is, say, in S3, the cyclic subgroup generated by, for example, the true cycle 1, 2 is not normal in S3. This has 6 elements, that has 2 elements. Why? Well, for example, if you look at the coset, the left coset 1, 2, 3, with this subgroup, as a set it's going to consist of the products 1, 2, 3 with the identity and 1, 2, 3 with 1, 2. That will give you 1, 2, 3. The left coset containing 1, 2, 3 really does contain 1, 2, 3. This one, though, will be what? Do the calculation. Let's see. 1 maps to 2, which maps to 3. 3 maps back to 1. It's just that. 2 maps to itself. What about the corresponding right coset? I claim it's not the same. And in essence here, because this is not Abelian and the center is trivial, that shouldn't be surprising. This is the right coset containing 1, 2, 3, and it really does contain 1, 2, 3, but it contains something else that's not that. 1 gets mapped to 2, which gets mapped back to 1. 2 gets mapped to 3. Does 3 get mapped back to 2? Double check that. Yes, it does. And these are not the same. Seems like maybe in a non-Abelian group, if you got a subgroup of order 2 that's not in the center, it's not going to be a normal subgroup. But maybe subgroups of order 3 could. All right, have a good weekend.